Hello, my name is Edward Jin, and this is my second lab presentation for Physics 2211. For an introduction, I will begin to discuss the concept of gravity versus drag. Drag is the air resistance acting upon the object that is moving. In the case of this lab, the air resistance is pushing up towards the sky as shown in the picture presented. Now, gravity is pulling the object downwards towards Earth as is a force of attraction. Gravity and drag both make up the surroundings, while the paper ball in this scenario will be the system. Moving on, we are going to go over Newton's second law again. This law essentially states that the object's acceleration is dependent on two main variables. The variables being the net force being applied on the moving object and the mass of the object as well. The purpose of this lab is to examine the motion of an object, the paper ball in this case, falling from rest using tracker and analyzing the forces of gravity and drag through computational models such as GlowScript. Now here we have the equations that will be used in the lab in order to understand the premise of the lab as well. I want to also note a new formula that will be heavily important in this lab, which is the net force equaling the force of gravity plus the force of drag. Here is my video for the tracker analysis. Now here is my tracker analysis. As you can see, my choice of object was a paper ball, which is lighter than a rock. Using tracker, I modeled the movement of the paper ball when it began to fall from rest. I was unable to alter the orientation of the video, so the x and y values will be flipped. Although I cannot change the orientation of the video, I am able to flip my axis, so the results will still be the same. I also set the leftmost side of the video or the origin of the paper ball as the origin of my axis. This means that the x values I get will be positive, and I will have to turn these points to negative as the ball is falling from point 0, 0. Now here are my initial conditions for the computational model used. We can see that I set the mass of the paper ball to 0.0135. I set the ball's initial position vector to approximately 0, 0.194, and 0. Additionally, I've set delta t, or the size of each time step, to 1 over 60 as the tracker also increments by this value. The value of acceleration due to gravity has been set to 9.8, and the value for drag is initially set to 0 as we are not accounting for drag just yet. So here in the first part of my computational model, I utilized the position and velocity update formulas to represent the force of gravity, as there is no drag for this portion. Therefore, F net is equal to the vector as shown. As we can see, there is a downward trend that shows a likewise trend to the one we found in the graph from tracker. Now we have the second part of my computational model, where I start to account for drag. For the gravity and drag version of this model, you can see I have changed the value of b, the proportionality constant, in order to account for drag. I was able to find this value by using trial and error until I found the value that best fit the data from tracker. The position and velocity update formulas are still being used, but now they are accounting for drag. Now we will use the proportionality constant times the magnitude of the velocity ball squared, also multiplied by the magnitude of j hat. This value, along with the force of gravity, will be used to find the net force. In this graph, I have included all three models: the one from GlowScript with the gravity, the one from GlowScript with both gravity and drag, and the one from tracker. As we can see, the gravity and drag GlowScript model is extremely close to the tracker model, and the GlowScript model with just gravity has a faster downward slope. However, all three models seem to show a very similar trend. Therefore, we can come to the conclusion that although there is not too great of a difference, using the force of gravity and drag allows us to pull a more accurate representation of a falling object than if we were to have just used gravity. I also want to note that there could have been, and most likely have been, some human errors made along the way for the tracker, such as the orientation of my video and how fast I might have dropped the ball. Now, in order to answer the first question, I would say the gravity plus drag computational model would be the only model to predict the terminal velocity, as it incorporates drag and gravity, which are needed to make the net force of 0. In order to answer the second question, I would say the terminal velocity would be the same, because the initial velocity does not affect the speed, as it just gives a head start. To test this, I would just change the value for the initial velocity in GlowScript, and you would observe that the terminal velocity would stay the same.